Hi everybody, I'm gonna shortly present my poster, which is about some coupled data simulation experiment we do work on at the National Research Council of Italy, in particular the Institute of Marine Sciences. So the main motivation for this work is to prepare towards a strongly coupled data simulation system, which in preliminary work, here you have an example, they are proved to minimize forecast imbalances in a couple model. When I say couple here, I mostly refer to atmosphere and ocean. In this picture from a work a couple of years ago, we show on the left weakly coupled, so the propagation of analysis increment during the forecast step from 2 hours to 2 days in the case of weakly coupled data simulation and strongly coupled, where we assimilate one single observation of SST, so in the ocean, and we look at the increments on the atmospheric temperature. You can easily see that in the first, let's say, 1 day, the weakly coupled case is struggling to recover from the analysis increment in the atmosphere, basically producing spurious sensible heat fluxes, while the strongly coupled doesn't have any problem with that. The second motivation is about maximizing the exploitation of satellite data assimilation, in particular to assimilate sensors that are sensitive to the oceanic and atmospheric parameters, and also specifically for the ocean we are always used to assimilate geophysical retrievals and not observation as measured by satellite. This has been proved to be suboptimal, so to overcome this unnecessary intermediate step of the geophysical retrieval that typically use the same background in the retrieval scheme and in the data simulation, we then aim to move towards coupled data simulation of satellite radiancy. Okay, as I said, this poster is divided in 2 parts. Basically, the first part is about idealized experiment with a single column atmospheric ocean model, which is based on 1D version of Easy Earth, thus including NEMO and IFS in the atmosphere. And for this system, we built a variational data simulation system that includes that wind vector, the atmospheric temperature and humidity, and oceanic temperature and salinity as state parameters. From a large ensemble of 1D simulation, we built some background error covariance matrix, which includes cross-component covariance terms. And for instance, we look at the, in this case on the A figure, we look at the profile of root mean square error of ocean temperature when atmospheric radius on data are assimilated. So you see the orange, which is not visible, the black and the green line, which cover orange black, consider the control experiment and the weakly coupled data simulation, while blue and gray represent 2 different experiments with strongly coupled data simulation enabled. Whereas weakly coupled, basically in the analysis system, the background error cross covariance term are set equal to 0. You see that in particular for one experiment which has a different set of background error covariances compared to the blue, the impact is very large and basically mitigate all the error in the thermocline. And here in the second figure we look at the heat budget in this experiment, just to make sure that most of the impact is not a cumulative effect during the forecast step, but is basically coming directly at analysis time through the propagation of the radius and data information from the atmosphere to the ocean, thanks to the cross-covariance, cross-component covariances of the background error matrix. Next, we've been looking at some assimilation of brightness temperature observation from the Copernicus microwave imager that will be launched in the next few years. with a surrogate observation operator. And basically what we find that assimilating brightness temperature data instead of geophysical retrievals always improve the skill score by a number between 8% for all parameters investigated to 11 and 18% for Roshan parameter, meaning that there is preliminary, there is expectation that assimilating data in brightness temperature space could further improve the exploitation of this data. The second piece of this work is about experiment with a fully 3D model, which we develop at CNR ISMAR, and is basically a regional couple model including NEMO in the ocean, WRF in the atmosphere, and HD, the hydrological discharge model for the Mediterranean basin. With this system, we so far set up a weakly coupled data assimilation system, which is nudging in the atmosphere and 3D varying in the ocean. And we look here, for instance, in the second panel to the track of medicane, which is a tropical-like hurricane occurring in the Mediterranean region. So you see in black the observed track, in orange and blue the track with spectral nudging, in green and red with full field nudging, meaning that spectral nudging improves the representation of the track. Now the difference between the orange and the blue line is that in the orange there is also ocean data simulation switch on, and you can see that the impact is negligible. But when we look at the some skill score metrics that summarize the impact on the intensity of the medicane, and this is shown in the panel F, basically we see that the purple line is with the ocean data simulation and light blue line without. We see that we do have depending on the forecast lead time and on the specific parameter, we have anyway an improvement, meaning that the of course improving the estimate of the upper ocean and the associated heat content energy in the upper ocean improves the simulation of the medicane. And finally, we've been looking at relative impact of coupling and ocean data simulation on some selected metrics. Here I showed the decrease of root mean square error for sea surface temperature and sea surface salinity, and the increase of eddy kinetic energy from a simulation in the ocean, so no coupling with atmosphere, no data simulation. Then we add data simulation and coupling, and we end up with some results that show that decrease of SST root mean square error is mostly benefit by ocean data simulation. The decrease of sea surface salinity root mean square error is mostly benefit by the coupling through enhanced precipitation patterns, and the increase of eddy kinetic energy is contributed by both coupling and ocean data simulation. And we are currently working to extend this analysis system in the Mediterranean coupled model to a strongly coupled scheme where we extend the ocean data simulation to the atmosphere. I thank you for the attention, and you also find more information about references in the poster.